closely at a piece of chewing gum. As you pull the ends apart, the middle gets visibly thinner, until eventually it violently snaps. When we hear the word stress, we usually think of a bad day at work or a tight deadline. But a very real, physical version of stress is happening constantly inside the chair you're sitting on, and even inside the bones in your legs. Physical stress is a measure of exactly how hard the atoms making up a material are being pushed together or pulled apart. Imagine two people playing tug-of-war with a thick rope. The tension doesn't only exist on the outer surface. That pulling force is distributed evenly across the entire thickness of the rope, forcing the fibers to grip one another. That internal tension is what keeps solid objects intact. Stress is the atomic grip holding the physical world together, preventing it from breaking apart under pressure. Force interacts with solid matter in three primary types. First, tensile stress, where atoms are actively stretched apart. Second, compressive stress, where atoms are violently squeezed together. Finally, shear stress, where sections of a material slide past one another. To calculate any of these stresses on paper, engineers take the total applied weight or force and divide it by the original thickness, or cross-sectional area of the material. That calculation gives us what is called engineering stress. Engineering stress is a baseline metric that uses an object's starting dimensions to predict if it will hold up to a specific load. But there is a dangerous flaw in the engineering stress formula. It relies entirely on the material's original thickness, which becomes an illusion the moment a heavy force is actually applied. Think back to that piece of chewing gum. As it stretches, it experiences something called necking. Necking is the physical process where a material undergoes a localized reduction in its cross-section, getting significantly narrower in the middle. As that middle section rapidly shrinks, the amount of pulling force doesn't drop. Instead, all of that load is squeezed into a much smaller, significantly weaker space. This chart shows a tensile test. The solid line represents engineering stress, making it look like stress decreases before breaking. But the dotted line shows true stress, the actual force divided by the shrinking area, which skyrockets upward as the material thins. Engineering stress tells a clean, mathematical story based on the past. True stress reveals the messy, accelerating reality of what is physically happening inside an object right as it fails. If we design our infrastructure assuming the original shape of a steel beam or a thick cable never changes, the things we rely on every day would fail without warning. It would be like trying to budget your current life based on the income you had 5 years ago. The math might look fine on paper, but the reality of your shrinking resources will quickly catch up to you. By tracking true stress instead, scientists can accurately map how a metal or plastic behaves, millimeter by millimeter, right up to the exact fraction of second it shatters. Mapping that precise breaking point is what allows us to construct airplanes with wings that flex safely in heavy turbulence, suspension bridges that carry thousands of cars, and skyscrapers that sway in the wind. The next time you walk across a bridge or sit in a chair, you can trust that it holds you up because billions of atoms are successfully managing the true stress of the universe.